You probably already have an intuitive idea that the color of a solution is related to the concentration of stuff that gives it color. If we add food color to clean water, the more food color we add, the stronger the color. The water is called the solvent. The stuff that gives it color is called the solute. Chemists use a technique called spectrometry to determine the quantity of solute present based on the color of the solution. This lab introduces the principles of visible spectrometry without using a spectrometer. We call it ibolometric spectrometry. Here's a schematic of a spectrometer. On the left-hand side is a lamp. The lamp produces light, which is passed through a prism. The prism splits the light into the colors of a rainbow. A slit is then used to select out a specific color of light. That light passes through a cuvette. Cuvette is nothing more than a transparent vessel for holding solution. The light that passes through the cuvette is then picked up by a detector which records the quantity of light. Typically, one first measures the intensity of light when the cuvette is filled with nothing but water as a reference. The cuvette is then filled with solution, and of course the detector picks up less light. The intensity of light that reaches the detector can then be used to find the concentration of solute in the cuvette. Okay, so that's how a spectrometer works, but I'm guessing you don't just happen to have a spectrometer lying around your home. We have a way around that problem. Before spectrometry was invented, chemists would mix up a bunch of solutions with a range of concentrations. Matching the color of a solution whose concentration is unknown to one of those samples provides an estimate of the concentration. Today, we can be more quantitative about color matching with the help of a computer and drawing software. To be quantitative about color, first we have to know a little about how vision works. Our eyes have three different kinds of color sensors. One is for red light, one for green, and one for blue. Red, green, and blue, RGB for short, is said to form the basis of our color vision. Many drawing software applications allow you to set the color of an object using an RGB scale. Each color is assigned a value between 0 and 255, so a 3-number vector defines a specific color. 255, 255, 0 defines red. 0, 255, 0 defines green, and of course 0, 0, 255 defines blue. Any color can be represented by a combination of these three. If we take 1 times the red vector plus 1 times the green vector plus 0 times the blue vector, we get 255, 255, 0, and that's yellow. To set the color of this rectangle, select the rectangle, open Shape Fill, select More Fill Colors, and select the RGB scale. We'll set the values to 255 for red, 255 for green, and 0 for blue. When we click OK, we see that the rectangle is yellow. The combination of 1 times the red vector plus 1 times the green vector plus 0.39 times the blue vector yields 255, 255, 100. That's light yellow. We can see that by setting that color with the RGB vector. Again, select the rectangle, select Shape Fill, More Fill Colors, and set that to the blue value of 100. We can see the rectangle is now light yellow. We can give the color of a solution numerical RGB values by matching it to a colored rectangle in our drawing software. It's pretty fun to play with the color scale. I suggest you do so before attempting this experiment so you can get a feel for how the numbers relate to color. So what's the relationship between color and concentration? We have to do a wee bit of math here. If you miss anything, you should still be able to follow how the experiment works, and you can always come back later if needed. According to the Beer-Lambert law, Yes, that really is the Beer-Lambert law. The adsorbance of a solution is given by the molar absorptivity times the path length times the concentration. Molar absorptivity is an intrinsic quantity for a substance and is constant. It varies from substance to substance, but is constant for a given substance. The path length is a constant in the experiment as well. It's just the width of that transparent cuvette. The key here is that adsorbance is linearly related to concentration. The higher the concentration, the more light is absorbed. Now that's a nice linear relationship, but our eyes don't see the absorbed light. They see the light that isn't absorbed. They see transmitted light. The two are related. Adsorbance is minus log, base 10 log, of the transmittance. By substitution, the molar absorptivity times the path length times the concentration is equal to minus the log of transmittance. This gives a direct relationship between concentration and the amount of light transmitted through the sample. Here we have combined the constants into a single constant K for simplicity. Overall then, the experiment works like this. Mix up a solution of known concentration. Measure the transmittance. Compute the value of K. For a solution of unknown concentration, use this K value, measure the transmittance, and then you can compute the concentration. How do we find the transmittance? There's the transmittance for each of the basis colors, red, green, and blue. Record the RGB value for a cuvette with just water in it and call these values R0, G0, and B0. These should all be very close to 255. If a sample has RGB values of R, G, and B, then the transmittance for red is R over R0, the transmittance for green is G over G0, and the transmittance for blue is B over B0. In a typical visible spectroscopy experiment, one mixes up several standard solutions, each with a known concentration. The adsorbances of these solutions are then determined with a spectrometer, and the adsorbance is plotted as a function of concentration. So here we have an adsorbance axis, and here we have a concentration axis, and for each solution of known concentration, we measure the adsorbance. These data points giving adsorbance as a function of concentration are then fit to a straight line using least squares fitting. This best fit equation can then be used to relate the adsorbance of a solution to its concentration. We take an unknown solution, measure its absorbance, and using our best fit equation, we can determine the concentration of that solution. Here we would determine this calibration curve using just two measurements for the sake of simplicity.
For this experiment, you're going to need a computer, a clear transparent jar. If you have one with a rectangular cross-section, that's ideal. A juice pitcher, food coloring, or water-soluble colored liquid free of particulates. We used cranberry juice and beer. A long-handled spoon for mixing, plain white paper, and a place to carry out the experiment with access to water and a sink.
Mark your transparent jar with a small piece of tape so that you can measure out the same volume of liquid every time. We will call this volume 1 cup. It doesn't matter if it is exactly 1 English cup, only that you can reproducibly measure out the same volume of liquid. Fill your transparent jar with clean water. Place it in front of the computer screen and match the color to get the R0, G0, B0 vector. Record those values. It should be very close to 255, 255, 255. Before you remove the jar, mark its position with a pencil so that you can return it to exactly the same position every time. Fill your transparent jar up to the tape mark with water and add 1 drop of food coloring. Dump the solution into the pitcher. Dilute it with 2 more cups of water and mix. This solution has concentration 1 drop in 3 cups, or 0.333. Return the solution to the transparent jar. Place it in front of the computer screen and match the color to get the RGB vector. This is the most tricky part of the experiment. You need to very carefully vary all 3 color values to get a good match. Record these values. We will call this R1G1B1. Using these equations, compute K for R, then again for G and B. You'll probably want to set up a spreadsheet to do this. Now that you have the K values, you can predict the RGB vector for any concentration of solution in this solute. Dump the solution back into the pitcher. Dilute with 3 cups of clean water and mix. This solution has concentration 1 drop in 6 cups, or 0.167. Predict the RGB vector for this solution using these equations. Set the color of your comparison rectangle with these RGB values and compare to the solution. How'd you do? It should be very close. Try a couple more dilutions to convince yourself it is working and that you didn't mess something up. Here we take 1 cup of the 1 drop per 6 cups solution, concentration 0.167, and add 3 cups of clean water, giving this new solution a concentration of 1 drop per 24 cups, or 0.042. Again, we predict the RGB vector, set the color of the comparison rectangle, and compare to the solution. Looks good. Here is the real test of this method. Can you find the concentration of an unknown? See you later. I'm going to sneaky mix up a solution without telling my lab partner here what the concentration is. Let's see how well she can figure it out. Come on back. This is a fairly common situation in an analytical lab. You know what is in a solution, but not how much. Now the chemist here knows the solution contains red food coloring, so the RGB vector must fall on the color scale defined by these equations. She will guess a concentration, predict the RGB vector, and compare. If the comparison color is too dark, she will guess a lower concentration. If the comparison color is too light, she will guess a higher concentration. Lather, rinse, repeat until the color matches.